Hello everyone and welcome to another video. So today I'd like to continue our discussion on probability by looking at a very specific probability distribution function, namely the binomial distribution. So we're going to build off some of the discussion we had in our previous video where we discussed general probability distribution functions and cumulative distribution functions. So if you haven't seen this video first, please make sure you go back, watch this, because I'm going to build off some of that infrastructure today. So this binomial distribution shows up actually quite a lot. Things like games of chance where maybe you're rolling die, or maybe in quality inspection engineering where maybe you have a batch of parts and you'd like to figure out how many of those parts are defective. Or even things like medical trials where you have a large sample of people that are taking a certain drug and you like to see how many of those people are responding positively to that drug, and you want to calculate all these associated probabilities. So in this case, what we're doing is we're interested in the number of times some event A occurs in n independent trials. So in this case, our discrete random variable that we're interested in is the number of times that event A occurs in these n trials, right? So to do this, what we need to do is first assign or figure out or derive what is the probability of A occurring in a given trial. So let's just call that the probability of event A. Let's just call that P, okay? So we have that. You can obviously calculate then what's the probability of A not occurring, right? That's the probability of A complement. Let's call that the probability of B. So B is not A, right? So if A is a success, B is a failure. You can kind of think of it in that situation, right? So that probability of a failure is called Q. And since it's the same as A complement, it's just 1 minus the probability of A, right? So P is the probability of a success, or A. Q is the probability of a failure, or B. Let's just use that, okay? So we can obviously see that if we have these n trials that are happening, if A occurs in, let's call it X number of these trials, right? Then A did not occur in n minus X trials, right? So again, this is really simple. This is a situation where you either have a success or a failure. It's one of the two situations, but we've got n independent trials. So now what we're interested in doing is counting how many times did A occur in those n trials. So I think the easiest way to look at this is with a concrete example. So let's look at this example. So I've got a couple of daughters and they're playing a lot of soccer nowadays. So let's say you've got a soccer team, right? And they're going to play a tournament. And let's say that over this tournament they're going to play 5 games. And let's assume that the probability of them winning any given game is exactly the same, right? So like all the soccer teams have the exact same level of skill, right? I think it's obviously contrived for this example, but I think from an academic perspective, I think we can roll with that, right? So like I said, the soccer team is going to play 5 games. The probability they win any given game is P. I want to know what's the probability that over this tournament, they're going to win exactly 2 games, okay? So within the context of the binomial distribution, in this case, our n is equal to 5, right? That's the total number of trials that we have. It's 5 games they're going to play. They're basically going to roll the dice 5 times, and they're going to see what's the probability that they win any of these given games. So let's call the probability of a win. A win is event A. Let's call that P, okay? This is the probability of winning one single game, or a success, okay? Now, what I'm interested in is X is equal to 2. I want to know what is the probability that over this entire tournament, they win exactly 2 out of the 5 games, or there are 2 successes in these 5 trials, right? So I think the easiest way to do this is, if you remember back to our discussion on permutations and combinations, we can just basically write down or enumerate all of the possible situations that could happen. So here's situation number 1. They could have A, B, 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 meaning they win their first game, they win their second game, then they lose games 3, 4, and 5, right? This is one possible sequence that could happen in this tournament, right? Another possible sequence is they win their first game, lose their second game, win their third game, then lose, right? Et cetera, et cetera. So you can see that you can basically enumerate, these are all 10 of the possible situations that could occur in terms of the sequences of win-loss, right? So let's go ahead and just examine maybe one of them. Let's look at the sequence number 1 here to start with, okay? That's the easiest thing to do. So because all of these events are independent, right? The probability of that sequence number 1, right? It's just probability of A times probability of A times probability of B times probability of B times probability of B, right? A, A, B, 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 right? And again, remember, we called the probability of a win, or A, P. We called the probability of a loss, which was B. We call that Q. So this is just P, P, Q, 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 right? Or P squared times Q to the third, right? And again, we're going to remember here that Q, it's just 1 minus P, right? That's what we have over here. Okay, so this probability, let's write that down, actually over here. The probability of this sequence, the probability of, let's call it the sequence A, B, 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 right? This is P squared times Q to the third, right? And now, what if we do the exact same analysis for this, for sequence number 2? You can see it's basically the exact same thing. It's just probability of A times, and then I guess I got to change this to probability of B to be consistent, and then this is probability of A, right? But you can see all we're doing here is we're just shifting the order of the P's and Q's, and you still end up with this exact same expression, right? So this probability is also this probability of A, B, B. It's still P squared Q cubed. In fact, all of these things have this exact same expression, right? So what we see is that the probability of them winning exactly 2 games is I have to add this probability to this probability to this to this to this to this to this. So I'm basically adding up the probability of any of these sequences occurring, right? So I end up with basically, it's what? It's 10 times this number, right? Because there are 10 possible sequences. Each sequence has a probability of P squared Q cubed, right? So we end up with this, right? The probability of any of those sequences occurring is 10 times P squared Q cubed. And again, this coefficient 10, this is the number of possible combinations and permutations of this sequence of A, B, 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 right? So you could write this as this, right? 5 factorial over 2 factorial times the quantity 5 minus 2 factorial, right? This, if you remember, is the binomial coefficient, right? We talked about this earlier in our permutations and combination discussion, right? This is basically n choose x, right? It's 5 different trials and the number of classes is 2, right? So yeah, it's just n choose x, right? That's this coefficient here. And then if you look at this over here, the probability here, the P squared Q cubed, that's basically P to the number of, to x, right? We said x was 2, right? And then the coefficient of Q is just number of trials minus x, right? So you can see that this works for x is equal to 2, 3, 4. You could basically change x in this calculation, and we would get, this is our probability distribution function, right? It's just building up this sequence, and it's basically counting them all and calculating the probability of each one. So really, what we end up with is, this is the probability distribution that we're interested in, right? This is known as the binomial distribution. Sometimes this is also referred to as the Bernoulli distribution, right? And the reason it's called the binomial distribution is, I think we see it right now, is because we basically have the binomial coefficient, right? N choose x showing up right here, okay? So this is pretty much the probability distribution. And what's actually interesting about this is, maybe what we should do is, let me flash up like a screenshot over here, and let's plot this probability distribution, the binomial distribution, for this case of n is equal to 5. So that's what you see over here, and these are probabilities, there are 1, 2, 3, 4, 5 of these different graphs. Each one of these probability distribution graphs are for a different value of P. So the one on the far left, right, this is if P is equal to 0.1. Okay, so coming back to this situation, what we see here is that means that this soccer team is actually pretty bad, right? They only have a 10% chance of winning any given game, right? So over the course of this tournament of five trials, right, you can see that the probability that they win one game at least is kind of high, right? But the probability they win 2 games, that starts to drop off, right? And that's actually the value that we care about, right? This one that we're highlighting right now is the situation we're talking about in this specific example. But you can see as x increases, now I want to say, what's the probability that they win exactly 3 games, you see that goes down even more. And by the time you start asking what's the probability that they win 4 games, this is almost 0, right? Because this team is pretty horrible, right? They only have a 10% chance of winning a game. There's almost no chance that they're going to win 4 games. And you can see the number of 5 is it doesn't even show up on the graph, right? It's virtually impossible for them to win all 5 games because they're so they're kind of bad, right? But it's non-zero, right? It just doesn't show up on this graph. Now, as you start moving to the right, like let's look at the one in the middle. The probability is 0.5. Now they're this team where they're half good, half bad, right? It's basically flipping a coin at any given game. They have an equal chance of winning and losing. And you can see in this case, it's kind of reasonable actually that they could win. It looks like 1, 2, 3 or 4 of these games look pretty probable. And then if you move all the way to the right graph, right, that's a probability of 0.9, right? That's basically saying this team is almost unstoppable, right? In any given game, there's a 90% chance they're going to win. So actually what's interesting in the context of the case we're examining, you can look at this, that the probability that they win exactly 2 games is, again, it's very, very small, because they would have to get extremely unlucky to lose 3 games, thereby winning 2 games, right? Because how are they going to lose 3 games when they have a 90% chance of winning any given game, right? This is an unstoppable superstar team. They have to be horribly unlucky to lose 3 games, right? And as you can see, it's an interesting distribution, right? Okay, so with that, give me a second to erase the board, and let's look at oh, actually, wait a second. You know what we should probably do before we erase the board? Now that we see this probability distribution over here, what we should also maybe talk about is, let me write it down here. I kind of ran out of space next to it, but we should talk probably about what the mean and the variance of this distribution are. Okay, so in the interest of time, let me just write this down. You can show that the case is, in fact, I think we have a homework assignment on this, that the mean of this binomial distribution, it's really easy. It's just n times p. And then the variance of this is just n times p times q. And again, we know q is the same thing as 1 minus p, right? So here we go. Here's the mean and the variance of this binomial / Bernoulli distribution, right? Okay, so now that we've got that all characterized, let's go ahead, give me a second to erase the board, and we'll look at one more example. All right, let's look at another example of rolling a fair die 4 times. And what I want to do is I want to calculate what's the probability that I obtain at least 2 6s during this game. And actually what we should do is, let me underline this thing where it says at least. So what I mean by that is, let's look at, for example, here's one play of the game. You play this game 1 time, you roll it 4 times, you get a 1, 4, 6, and a 3. So in this case, you only rolled 1 6, so that you didn't win the game, so to speak, in this case, right? Because you need at least 2 6s. Now, here's another game on this row. You get a 2, 6, 1, 6. And in this case, you do roll 2 6s, it looks like. So in this case, you do win, right? So this is a win, right? Now, we also have to consider the case, what about this third game? What if you get a 6, 6, 4, 6? This time you get 3 6s. Since I want at least 2 6s, this is also considered a win, right? And et cetera, et cetera. You could also get all 4 6s if you got super duper lucky, and we got to take that into account, right? So within this context, let's go think about how can the binomial distribution help. So let's go ahead, and first of all, we're going to consider rolling a 6 as a quote-unquote success or event A, as we talked about earlier. So the probability of rolling a 6 is obviously 1/6 because this die here that we're playing with is completely fair. Therefore, the probability of not rolling a 6 is 1 minus A, or 1 minus a 6, so 5 6, right? Again, this is pretty simple, right? This makes sense. Now, all we have to do is basically break out our discussion on our binomial probability distribution function. In fact, I left it down here in the board. This is the same thing we wrote down earlier. We just need to apply this now to our situation. So we need to compute this PDF at x equals 2, right? Because that's going to tell me what's the probability that I roll exactly 2 sixes in a game, right? So that's a probability that I want this random variable to be 2. That's the PDF, the binomial distribution, evaluated at a value of 2. So it's just basically, I just need to plug all this in, right? So there are 4 trials, 2 is the x that I'm interested in, just plug things in, right? So it's 4, whoops, sorry, that should not be, that should be not a line, sorry. That should be 4 choose 2, right? This is our binomial distribution, right? Times p squared q cubed, right? So you basically plug in all of our numbers and we get 25 over 216. And again, this number tells us what's the probability that we obtain exactly 2 sixes during our game. Now, because we need to look for at least 2 sixes, we also have to look at what's the probability that I get 3 sixes, right? So that's this guy here, probability that x is equal to 3. It's just the same PDF, but now x is 3, not 2, right? So again, all I need to do is just update my formula. So now the binomial coefficient becomes 4 choose 3, right? P to the third times Q to the 4 minus 3, right? Just plug in all your numbers, and again, you get a lower probability, 5 out of 324, but this is the probability that we obtain exactly 3 sixes in this game. And then we also have to compute the super duper unlikely probability that you get all sixes, right? So again, that's just the PDF at x equals 4, right? So it's 4 choose 4, yada yada, you do all this thing. This is, you know, as you can see, this is super low probability, but there is a chance that you could get super lucky and roll all 4 sixes, sixes all 4 times, right? So it's 1 in basically 1,300, right? But because the problem statement says I need to find at least here, right? I need to look at the total probability of what's the probability that I get 2 plus the probability that I get 3 of them plus the probability that I get all 4 sixes. So I need to add up all of these probabilities, right? So if you do that, you come up with this number, which is about, I don't know, 13.2%. That you win this game over here where you have to roll at least 2 sixes to be considered a complete win of this game, okay? So I'll tell you what, let's run over to MATLAB real quick and let's write a simulation of this situation just to check if this analytical solution is correct. Alright, so I've got a really simple MATLAB script set up to simulate this really simple game. So all we're doing here is we're defining a bunch of weights for this function that I made called roulette wheel. So this function here is supposed to basically simulate spinning a roulette wheel where you can specify how large each slot is. So I want to do this so I can basically simulate how to throw a fair die, right? Where each slot of the roulette wheel is 1/6 of the entire wheel. That is basically going to simulate throwing a fair die with 6 sides. I'm going to make both of these scripts, both this function roulette wheel and the script that we're going over right now are actually available for download. If you go to the description of this video, you should be able to find both of these files, and then you can use them for any situations that you might want. So for example, this roulette wheel is helpful if you want to be looking at situations where maybe the die is unfair, or maybe you have a 20-sided die, or things like that. You can play with it a lot. But what I'm doing right here is basically saying this is a die with 6 sides, or it's a roulette wheel with 6 slots, and each slot is equally likely. So again, this is basically setting up for a fair die. Now, we said n is equal to 4, right? This is the number of trials in one single game. I'm going to roll the die 4 times, right? And now what I'm going to do is I'm going to basically set up a giant for loop where I'm going to play this game. In this case, I guess I set up for 100,000 times to play this, okay? So all I'm doing here is let's just make some kind of counter where I'm going to count the number of games where you have at least 2 sixes, okay? And now all I'm going to do is I'm going to initialize this to 0, and then in the main loop of this, I'm just going to play this thing 100,000 times, right? So what I do is, let me just go ahead and put a breakpoint in here, so just so we can see what's going on. Let me run this thing to this point. So all I'm going to do is I'm going to spin this roulette wheel, and I'm going to spin it 4 times. That's what I'm doing here. So this thing called results, let's go take a look at this. So in this case, I got a 5, a 2, and a 1, right? So all I'm going to do then is I'm going to find how many sixes are there in this results vector, right? And then I'm going to count the number of them, right? So this tells me how many sixes I get. So in this case, this should be 0, right? So if I look at this, this should be 0. Yeah, so I didn't win this game. So all I have here is I've got an if statement that if you do have more than or equal to 2 sixes in your hand, so to speak, we're just going to increment this counter, right? So again, this is really stupid and simple because it is a simple game, and all I'm just going to do is just run this a whole lot. So let me go ahead and stop debugging. Let me run this thing again, and it's going through it, and then I'm just going to, at the end, I'm going to count and print out the number of times we had at least 2 6s divided by the total number of games that we played. And look at this. It looks like it's 0.13256. I think our analytical answer was 0.131944. So I think these are really, really close. I mean, if I run this again, I might even get more lucky. I mean, look at that, right? So this is pretty much exactly a Monte Carlo simulation showing that numerically we get the same thing as our analytical results. So, all right, with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Remember, the new videos come out every single Monday, so I hope we'll catch you at one of these future discussions, and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.